sorry, I just need to open it one more time. Okay. So welcome to week 4 of introductions to PLCs. This week we are going to go over some new concepts for us, some things that some of you guys have probably seen before. So what are contacts? So normally open contacts, normally closed contacts. You've probably seen this in relays, relay logic, electrical drawings. If you've done Boolean logic before, and for AND and NAND gates, similar concepts. We're going to look at extracting system values from these PLCs. So these are your GSV and SSV instructions. These are get system values and set system values. For the Logix 5000 platform, it is different from the Logix 500 platform. And I might be able to show you some examples of how you would do them in both. Then with the get system values, we're going to look at minor and major faults, kind of the difference between them and how you could monitor for them, even how to look up what those faults are. Yeah, in a perfect world or imperfect world, maintenance doesn't really need to get into some of the machines unless something's faulted. So if the only time you end up interacting with PLCs is when they're faulted, this is important to know how to do. And then I know we went through some basic scan orders with the PLCs, and we're going to add an extra layer to that in fault handling routines. And then again, major fault records, how they work, where to find them, how to decipher some of them, and then I'll log into one of the PLCs and I'll fault it. I believe, yeah, the emulators should be able to fault these. So we'll be able to monitor that, show you how to extract that data. And there's some other stuff that you can extract with the get system values too. So this off the bat, normally open and normally closed. So anybody who's worked in automation before, you've probably heard this, and you probably interact with these contacts all the time. So normally open contacts are contacts that in their base state are open. So the circuit is not complete, whether that be the example on the screen here is a proximity sensor. You can see that the switch here is open. So hence normally open. So in their normal state, your digital input would be off or 0, or if you're looking for voltage, it would be 0. When the field device changes state, such as this proximity sensor here, it would then close the contact, and then that input would become 1 or high. So the proximity sensor, this normal state is open. It detects something, the state would move to closed. There's a fancy animation. This is for almost any device that'll have contacts on it. So motor contactors, your run status, your fault contacts on devices. Normally open is just you expect it to be the input to be low and close when the signal is active. Any questions? Perfect. Normally closed. So we're looking at the opposite of normally open. So in their resting state, they are a complete circuit. So in this example here, we have a smoke alarm. So they will send a 1, or the input will be true in the resting state or the non-alarm state. Most normally closed circuits are for some sort of safety or fail-safe signal. Smoke alarms, gate contacts, floats, something that if the wires were severed, you would still want to know what was going on. So for this smoke alarm, so then when the signal changes state or there's a disconnect in the wire somewhere, we would get an alarm. Or the status would indicate. So a 0 state would be an alarm. Does that make sense? So for this fire alarm, the normal state is closed, no smoke, no heat. The alarm state would be the open state. So the toast moves towards the fire alarm, the signal would open up, you would get the PLC would then see a transition from 1 to 0 or true to false, and then you'd issue your alarm. So these could be weight sensors. Dead man switches are a little different because sometimes dead man switches are actually normally open, where you hold them shut. And does everybody know what I mean by a dead man switch? I don't know where the chat is. Where'd my chat go? Yeah, I'm seeing lots of yeses. Okay, perfect. So depending on the actual hardware for the pendant, the dead man pendant, it might actually be a normally open contact that you're holding shut. And if you were to release it, it would open up again. So there's different applications, and depending on how they're being used, would be how, depends on how it'll be wired. And there's also a lot of devices that'll have both contacts inside of them. So if you look at a relay, you'll actually have a normally open or a normally closed contact for the same coil. So you could wire it up the way you needed to, depending on what devices were connected to it. All right. So the next topic here is get system values. So anybody who's seen I'm gonna start working on connecting into the college network. Sorry. Anybody who's worked with some of the Logix 500 processors, inside the configuration, there's system tags that are just very easy to find. In the Logix 5000 environment, most of that information is there. It's just you have to run this GSV, or get system value, to be able to pull it out. So you have to request it. So what's on the screen here is logic that there's a timer that runs, and every 5 seconds or 5,000 milliseconds, it will gather fault information. So it'll log into the program class the main processor, it will seek out the major fault record, and then it will put that major fault record into the tag you've defined for it. So this destination tag would be a tag that you would assign. So anytime you want to look at fault handling, pull fault information out and use it inside of your program, you need to extract it. If you are only logging in to view some of these, why something's faulted, there is another location to find that fault information, and I will show that to you. But if you need to pull this information to look at a fault in the controller, you have to use GSVs. So again, the ladder logic above here will scan for a major fault record every 5 seconds. The timer runs whenever the timer is not done. So if the timer is not complete, it runs. Once it's done, the next rung will grab the fault information, and then the next scan, the timer will reset. The timer done bit for the free running timer. So this is a good way to, this is a very frequently used method of doing something at specific intervals. So you'll use a timer to reset itself and do a very specific task every so often, whether it's get system values, store specific data points, load averages, do math sometimes. So any questions?
Hey Ryan, sorry, this is Addy.
Yep.
So in this specific logic, you're using the done bit is used. But then when you also have an enable bit. So is the enable bit on when the timer is running, or the enable bit only comes on once the timer is done?
So this right here will turn on when the timer is executing. So for this rung, when the timer is not done, this EN will turn green and it will be enabled. So when it's enabled, the timer will time. So the preset is the length of the timer, and you would see the accumulator here counting up. Once the accumulator equals the preset, the done will become true. Once the done becomes true, this is, because this is a examine if closed, becomes, this side of the contact becomes false, this side becomes true, and then it will execute this get system value. And then it will reset. So for the rest of that one scan, that will be done, then it will reset and this will start again. And then 5 seconds or 5,000 milliseconds later, it will cycle again. Did that explain that?
Yeah, thanks.
So the opposite of the get system value is set system value. So the set system value can be used to do a number of things. It can be used to clear some faults. Not all faults, but it can be used to clear some faults. So in this instance, this ladder logic here will test the fault information coming in. So the rung that we saw before moved the fault code into a specific tag, and this will monitor to see if the fault code equals a specific value equals EQU, then it's going to move 0 into another tag, which is actually clearing the fault code. And then it's going to set the main fault history back into the program. So you can use this in the event that you have a reoccurring fault. you can use the controller to monitor for specific fault codes and then clear that fault. Does that make sense? Sorry.
So the SSV basically, it's just recording what the fault was after we have copied a value to the fault history, correct?
Not quite. So here it's in these rungs here, every 5 seconds, it will get a value from the system. So the processor, if it faults, if there's a fault code in it, at the end of this 5 seconds, it will extract that fault code and write it into this data array. Then in this rung, it will monitor that data array. And if that data array has a specific fault code, it will then write 0 into the data array. And then this will set 0 back into the fault code. And this would clear that specific fault.
So the SSV clears the specific fault.
For this,
Or-
yeah. So the get system value will reach into the controller, or in this case, it'll reach into the controller, pull out a system value, and the set system value will set the system value. So the example being used here is for fault information, but this can be used for pulling the system time out of the processor or setting a new system time in the event that the system time is deviated. You can get fault information from communication modules as well. This doesn't only work with system values for the processors, but if you were to have any module really, so if you had a fault on a digital input card, you could set that fault, you could clear it, you can pull that information to monitor the status of comms modules. So the get system value is reading, but because you can't look at the system values directly, you have to request it and write it into tags that you create. And then if you wanted to clear alarms or set a new time, you have to set system value. So you're writing into the system values. Does that help?
Yeah, I thought the move command itself would set the system value, because technically the move command is basically removing a value 0 into the data array. So then that technically is the resetting of the value, right?
So it moves the 0 into the data array. That's correct. But the data array isn't in the processor. The set system value would then take that 0 and push it into the system value. So that would clear the fault. So
Okay.
it's kind of you need the get system value is pulling it from, if you imagine it as a drawer, the act of removing the data from the drawer is the get system value. When you're looking at it, so when you evaluate the data you've pulled out of it in the equals, and then you can throw that data out, and when you put the data back in the drawer, the SSV is putting it back in the drawer and closing it. Might be terrible with metaphors. Does that help anybody? Is anybody confused? Because this is kind of different than the way it's done with the Logix 500. All right, sorry, I'm just looking at the chat to see if anybody's gonna. Sorry. So GSVs get system value, retrieves a system value from the PLC's internal system memory. It's used to retrieve, again, alarm information, date, time, and information, communications information. There's a whole gamut. I'll show you with some of the code. There's examples of all the different types of information you can get. And then the set system value will write system values into the PLC's internal memory. So used to clear faults, set date and time. Yeah. Again, yeah. So I'm connecting into the college right now to get some code up. So we'll go through an example. Thought I was connecting into it. No, I guess we'll go over. Sorry. Haha, you guys are all in. Okay, I'm gonna have to do that in a bit. All right, so minor faults. So has anybody dealt with or had the nightmare of going through troubleshooting faulting processors? How do we know where the faults are in the ladder logic? That is not a dumb question at all, and I will show you how to look at that. It is coming. Pardon me. And yes, and some examples are coming. So minor faults and major faults operate differently inside the logic. So a minor fault does not halt logic execution, and it can be cleared inside a fault handling routine. So that get system value and set system value to clear faults only works with minor faults. So that's going to be arithmetic overflows, some card faults. We'll go through a couple of examples of minor faults, and we'll look at a listing of all the different fault codes you can see. But the basics of it is, if you're looking at the front of a processor, if all the lights are green, there are no major faults. If you have red lights, you're going to have a major fault. So major faults, they stop the processor. You might as well put the processor in the program. Logic halts, all outputs turn off, inputs stop being looked at. The controller switches into a faulted mode. So if you've ever looked at the front of a PLC, there's a run light and an OK light. Those are going to be red. These can be cleared. Sometimes can be cleared in a fault handling routine, but not always. And I know that's very vague, and it all depends on what's happened. So if there are any red lights on the processor, you need to investigate which lights are red. And I know this would be better if we had physical processors in front of us. Unfortunately, we don't. So as you can see in the graphic here, there are 4 lights on the front of the processor. So there's a run light, there's a force light, there's an SD light, and an OK light. So the run light is, if it is red, the processor has faulted and is not executing code. If that light is green, it is executing code and everything's fine. At least it's executing code. Something might not be right, but the processor, there's not something that is causing the processor to fail. If that light is just off, your program, the key switch might be in program mode, or you might have put your logic into program mode. In which case, just going online and putting it back into run might turn it back on. But if it's red, logic isn't being executed. That force light. So forces are used by programmers to set bits or values to specific values that override process logic. I try never to use them. In some cases, you have to if you're troubleshooting other code and you don't want to edit it. You can force outputs on or force outputs off. Better practice would be making logic changes to kind of prevent the code from turning things on. Forces do have to be enabled to work. So if you're in there modifying code anyway, forces can be a powerful troubleshooting tool, but they can also really wreak havoc on logic if you're not careful. The SD light, sometimes it will fault a processor. These processors have an SD card slot in the front of them. Sometimes that SD slot is used to store a copy of the program. Sometimes it is used to transfer data onto from the program for backup logging. It can also be configured to automatically download the latest copy of the code onto the processor in the event of a fault. I can show you, I think the emulator will let me show you where you might be able to see that. But again, a really useful tool, but also very dangerous, because if you use that feature for a controller and you fault it, it might write a very old copy of the code if you don't keep that SD card up to date. And to load that SD card, you have to put your processor, you have to take it out of run mode. So if you're running a process that can never stop, if you can't have your processor go into program mode to load that, it's not likely that people are going to keep backing it up. So that's an aside. I'm sorry. But it's a good thing to have it in your pocket, because more than once I've shown up to facilities where they say, oh, the process just stopped working, and we found that the SD card had loaded up a very old program, but there had been many edits. So we ended up finding a current copy of the program, downloaded the current copy to the machine, and everything started working again. We had to just update the SD card and then prevent it from automatically downloading the old program on a fault. Oh, sorry. And then there's the OK light. If the OK light is red, a major fault has occurred. Solid red. If there's a flashing light, it might be a minor fault. But again, a very quick indication that the program's not running and you fault the controller from the outside. Just looking at it, you can see if it's faulted. Any questions? I know I just kind of threw a lot at you, and without a processor in front of you, it's kind of hard to envision this. So in your main program, and everybody is familiar with this layout, the tree, we've got our main task. So as we went over, I don't know if it was last week or the week before, the main task is scanned or executes code every cycle scan. By default, it's going to run the main routine every time, every single cycle. So if this scan lasts 100 milliseconds, then the main program, the main routine will be scanned 10 times every second. So the main routine is automatically, like, it will always scan this routine. Anything else, so any subroutine other than the main program, has to be called. So I know I touched this briefly with a logic demonstration, but if you want to have separate ladders to look at your input, output conditions, and process, like your logic, you have to put jump to subroutines for those ladders to execute code. And then they will be scanned every time the main program, the main routine is run. Does that make sense? Okay. So again, every scanned cycle, the main program is run. If in the main program you've got jump to subroutines for your input conditions, process conditions, and output conditions, then those will be called, and they will be called in the order they are in, like you put them in. So rung 0 will be called, input conditions will then be jumped to, all of your input conditions will be scanned, it will return, it will then jump and run process, and then it will run output conditions. So the curveball here, what we're touching on, is the fault routine. So the fault routine doesn't always exist. You have to create a fault routine and you have to configure it. So we're calling it fault handling, and you can see it here. If you are using this feature, it will only be scanned one time when there is a fault detected. So inside the fault routine, this is where we would put the logic that I went through earlier. So if instead of putting in that check for a process fault every 5 seconds, we can use the processor to monitor itself. And if there's a fault, we can then get the fault information. And if it's a very specific fault, we can automatically clear it, possibly preventing a major fault. So the fault handling routine here would use the GSV and SSV to read the fault information and automatically clear it. So that's just repeating what I already said. Does that make sense? And how it would only run once. There can also only be one fault handling routine per program. And we'll get into configuring that. So again, this is good for knowing about faults you would expect or something that's reoccurring if you have these happening in a system that you are trying to fault find. This could be when the fault is cleared. So you can keep it in logs, but you would have to code that, and you'd have to configure a data array. So you would use a data array every time you saw a fault, push the array down, and then you could look at some historical data, possibly pull that with an HMI system. There's no real historical log in the controller. There is a spot where you can see some of them, but if you clear them, they're gone. They don't stay forever. And I'll try to show you an example of that. I might have an example of that. So again, fault handling routines are useful for executing logic when you expect a specific thing to fault for the controller and you want to reset that so that your process can keep running. Automatic fault routine is only meant for minor faults. So there is yes, normally major faults don't have can't be automatically cleared. Normally, there is another main processor fault handling routine that can try one more. I'll show it to you. It just won't run on an emulator. I know. I'll get to that. But yeah, typically this is for minor faults. The fault handling routine is only scanned once. Since the fault handling routine is only scanned once, it's important to remember your order of operations, that it scans top to bottom. So if you were to put the clear your fault before the get your fault value, you wouldn't clear the fault. Does that make sense? So fault handling routines can automatically clear faults. So this is ignoring array faults during pre-scan or ignoring module faults if the slot's taken out. And I'll show you what that means in a configuration. I can't simulate it. I might be able to simulate it. So it can clear major and minor, but some major faults it can't. And I know that's vague, and it's not that it's arbitrary, but it depends on it really does depend on what the fault is, if it can clear it. So major fault record, where is the fault record stored? So there's a data array in the processor. It's 11 element array. That just means that there's 11 words. Sorry, they're actually bins. Where the data can be pulled from. So when you do pull this information, you have to pull it into an array of dints. You can't pull it into a single dint because it'll overflow. It can actually cause a minor fault. So the fault code and fault type are in word 2. So you can see where it's laid out. The information for where this comes from will be in the manual for the processor. All of the processors, I believe, are the same. If there's a change, sometimes you do have to dig through the processor manuals to see how they've programmed the data arrays. They might change from time to time. So this get system value pulls again from the program, the main program, the major fault record, and then writes it into main program fault history 0. The square brackets 0 is just the first word in the data array. And then the value for that is the 2228228. So the fault code and type are in word 2. The decimal value for that information, and then broken into binary. What is the fault code? I'm not going to make you do the math. So this information can be extracted out. You can do this math in the processor if you want to know the specific fault code. You would program the specific decimal value, or typically I'd always program a specific decimal value if there's a known fault condition that keeps reoccurring if you need to clear it. But this 34.4 fault code is important information, and there's another spot you can normally find it, but this is actually going to be found in a table for in the help files or the manual for the processors for troubleshooting. So if you're going to pull this fault information, you can then look it up and figure out, why is my processor faulting? And that's the whole point of this. Is, again, if your first interaction with a processor, you're working for an integration company or you're part of maintenance, and they say, hey, this line's down, and you go down there and the processor's faulted, the first thing you're going to need to do is get online with it and figure out, why is it faulted. So all of the information on how to extract the fault code, sometimes it'll be done. I've pulled the fault code information out and I've conditioned it in an HMI to display the binary to decimal fault code information like this. And you can see here a 34.4 type and fault code is a timer instruction as a negative preset or accumulated value, and that will fault the controller sometimes. So the fix is, you cannot load a negative value into a timer preset or accumulated value. And this might sound pretty straightforward, but sometimes operators, if you need to change a time delay or a length of time for something, the display value might they might hit 0.1, but the point is actually a negative, and they might write in -1 and fault the controller if it's not programmed to protect itself. Any questions? This was my last slide. I'm going to load up some logic and show some examples of this in the emulator. So if you guys want to take a break, I'm going to pause the recording. I'm gonna go get some more water, and then I'll come back and show some logic. No questions? Okay. I'll say 5 minutes. Back at roughly 5 after 7. So a couple of people have messaged me saying that when they log into the open access computers, they don't have the software required. I phoned IT today, and I logged into a number of them, and IT in their infinite ITdom says all of the machines on Cambridge Open Access have the required software. So if any of you log into a machine and it doesn't have this Rockwell software shortcuts, this is all of the emulate software that you need on this desktop icon. Take a screenshot which will include this, or even the RDP connection for the specific machine. And then either send it to me or send a ticket to IT and say, hey, I need the Rockwell software and it's not on this machine. But IT just said and reiterated that all of the open access machines have it. So anybody who's having issues, I'm sorry. As you saw, I also have some issues, but just make sure you're on the Cambridge open access ones and not the electronics or Cambridge anything else. It has to be these open access ones. I hope that clears up any issues. Computers are the worst part of my day, always. Okay. So in this week's notes, there is an example program which has that fault logic in it. Now, I do believe it is designed for an emulator. Let's hope the emulation logic works. Oh, you gotta be kidding me. Okay. So I'm not gonna mess around with that too much. I am just gonna restart. So the other thing is I asked them about that emulation issue, and they said that if somebody else uses the emulator and then they don't restart the machine, it will lock up that license. So rebooting the machine is the solution to freeing up the license and getting access to it. Okay, it looks like I have a working VM. It makes you feel any better, it's not just you. I reached out to some people, some other professors I know who teach at the college, and it's continual, the struggle.
Hey Ryan,
Hey,
can you show us how to add a processor to that emulator there on slot 0? Because last week when I was doing this, there wasn't anything in there and I couldn't go online.
okay. Well, I already have a processor in slot 0, but let's see here. So if you create a module, you can only, where the heck did it go? So you can only add either emulation modules or these sim 32-point input output cards. So if there's nothing there, like I can't add anything into it right now, last week, was there anything in slot 0, or was this RS links in slot 0?
So for me, the processor was in slot 2.
The processor was in slot 2.
Yeah.
So you can have, so the really neat thing about this emulator is it emulates a bunch of processors. So the only thing I've used this a lot for in the past is if I had like a plant startup with like 5 or 6 different processors, and you just, it's almost impossible to be like to have 5 or 6 ControlLogix processors on hand for simulating an environment like that. That's like, geez, 80 to 100 and $200,000 in processors. They are very expensive pieces of hardware. So you can, if you just go create and pick your slot at slot 4, it'll, well, sorry, you've got to actually select the processor. Slow. And then your firmware. So the firmware is specifically about the programming software. And I think the programming software on these machines is all 30. Remove programs. I could be wrong. I'm just trying to see what firm, if this will list all the different versions of the software. So there's 20. And it's Studio 30. Okay. So you could add and use 20 or 30. And that should be it. There. So it should be that easy. Right click on the processor. Yeah. And then run. So now it's you can see here, you know, I was talking about in on the slides about the lights. You can put them into run simulate here. So yeah, if you want a processor in a specific slot, you can just add it there, or you might even be able, like, and I should be able to download to either one of those. Actually, I can't. So this is the program that they gave us is actually for a GuardLogix controller. So we don't actually have access to the GuardLogix controller. So I'm going to change this to an emulate controller version 30. So this warning, so you know how I was saying that some of the, not all the processors are identical, especially with the safety ones, because that GuardLogix has this safety routine in it, which is actually not going to be used for what we're doing. They're not compatible. So if you switch from one controller type to another, there are some features that may or may not be available. If you have programmed features in one that isn't available on the other controller, your controller just, it won't work. So in that case, if you don't know if it's a live controller, don't just make that change. Make sure you have a copy of what you're moving from, because you can see here the controller you saw before, it had safety in it, and it was like a safety routine with some red stuff on it. This is neat. I kind of expected it to move it into an unscheduled routine, or even completely delete it, but it actually put it into a periodic routine, which was kind of neat. I didn't expect that, and now it's not responding. Oh God. Wait. Okay, so that is how you change the processor type. I know that was quick. Did everybody kind of pick up on what I just did there? So because the controller, the program that I had the wrong controller type, I couldn't just download it into the emulator. Version 30 might have been smart enough to tell me that I needed to convert it. But some of the older ones will just say you can't download a Ford into a Maserati. It's just not going to work. That's maybe also a really bad metaphor. But I'm a dad, so I'm entitled to them now. So slot 0 is the slot that you want your processor to be in. For the emulator, if you have multiple processors in here, you could actually just increment this up to 4 if you wanted to. Did that answer your question? The emulator is pretty straightforward. If you were having issues with it, try restarting the stupid VM. Yeah, okay, perfect. So again, comms, go online. We're looking for the virtual backplane. Somebody's got an emulate project 1 in there. I'm gonna upload that. Let's see what somebody else is working on. And this will be a good example. So somebody's got project 1 emulator studio loaded on that controller. This is saying, hey, connect to this controller. Our offline project is something else. Well, I don't have anything that matches that, so I can select a file. I wonder if it'll just let me there, projects. I'm gonna go to desktop, create a project that's called project 1 ACD. Oh, let's go here on the desktop. Will that work? No. No, doesn't want to do that. Let's see if I have a blank controller. I'm surprised that controller holds the emulator held a program. So neat. It's not letting me upload it. No. Oh, well, that would have been neat, but it's not letting me upload it. Sorry. And this is another reason why you have to save all of your files off the computer. Because if you didn't have a version of that software himself, or she, whoever they were, it's gone now. We have errors. Oh, was this not? Oh. What the heck? Yeah. Sorry that took so long. So, fault handling. So first, we've got main task and main program. Oh, we faulted. Great. We'll get to that. So when you set up your main program or any of your programs, whether it's a safety task, inside your main task, you can have multiple programs. That one's called. So you can create secondary programs. By default, you do need to configure main and fault. You can configure main and fault routines in here. So a fresh new program has nothing configured. And that won't do anything. Here in the main program, you'll see main right here. So as I said a bunch of times in the presentation, when the main routine runs, its main program is executed every single time. So main program typically will say main, but it can be configured to be any one of those. It doesn't necessarily have to be called main program. Whichever routine, whichever rung is selected and configured inside of the properties for the program is going to be the main routine. So if you were to change this to output conditions, it's output conditions that's going to run every single time the main program is scanned. And because this main program is the one with the jump to subroutines, if you were to configure output conditions, nothing else would run. It would execute the outputs, but not the inputs or the logic. The same with the fault routine. So you don't need to configure a fault routine. It's not necessary, but if you do want one configured, you would do it here. So you create your ladder. That this one is called fault handling, and then you point your fault at it. So only then will it run in the event of a fault. So did this run? It looks like it might have. Let's see. So here you can see the get system value, the evaluation, the clear, and then the main fault routine. These were what was used in the screenshots for the presentation. If you're logging into a controller to find the fault information and you're not interested in logging it in any way or automatically clearing it, you can go here to controller properties and then go to the so in controller properties there's a whole bunch of tabs, and by all means play with them, look through them as much as you can. But under faults, you can see major faults and minor faults, and these will list them. Now, I know, I think it was Tatiana who asked if there's a log. This is that log. Now, this one's called so it pulled a watchdog fault. So, yeah, cool. So a watchdog fault is, how do I explain it? So the processor is watching its processes. Seems redundant to say it, but if the process takes longer than it's expected, the processor assumes something's gone wrong. So, so it's looking at scan times. What the heck? Which process faulted? So safety task faulted. It's not happy. Nothing ran. So if yeah, so here it has a watchdog timer of 20 milliseconds, and it took 21 milliseconds to run, even though there's nothing going on inside of it. So for the time being, I'm going to inhibit the task. So inhibit means disable. And go okay. So now we can actually go up here if we want. Delete that rung so it's happy. And if we were to go to sweet. So you can see here the OK light is solid red. So if this were a physical processor, that would have faulted. Here the run light is off because the major fault has prevented the logic from running. It's no longer running. Now, this fault handling logic did not run. Does anybody know why this fault handling logic did not run? There are no bonus marks for answering this. Just throw out an answer if you think you know. It's pretty neat. Anybody? Wild guess. There's nothing to an no. One more guess. Okay. So this fault handling routine is only monitoring the main program. So when this program faulted, this fault handling routine did not care because it's not monitoring for a fault elsewhere. So you have these different programs will kind of run siloed. You can have a main task here with a main watchdog, but the safety task is separate. So you can kind of look at when you look at the tree, this safety task will end up having its own watchdog. The watchdog is a major fault. Do you want to allow? No. Oh, sorry. Sucks to be that guy. So the fault handling routine here will trigger if there was a watchdog fault for the main program, but it didn't catch the safety one. Okay. So if we look up here, again, we can see code type information. And if we were to look in the fancy F1, so if you need to find information troubleshooting inside of Rockwell, as long as the person who installed the software installed all of the troubleshooting libraries, the help menu F1 will open up the help menu, and it's getting better as well, where I'm looking at the major faults tab and I hit F1 and it opened up the major faults tab. So you can actually, I might even be able to find the controller faults lookup information very close to what I was looking for. Major faults tab. No, it's not perfect. So this is the screenshot from the presentation, but we have a different one here. So it was a type 6 code 1. So type 6.1. So task watchdog. So user task is not completed in the specified period of time. A program error caused an infinite loop, or the program is too complex to execute as quickly as specified, or a higher priority task is keeping this task from finishing, trying to do too much with a single controller. Wow, that's a dig. Huh, that's funny. Increase the watchdog timer, shorten the execution time, make priority higher. So there's a lot to unpack in that explanation. So essentially, the watchdog timer is a configured alarm. So you tell the controller how long the process can run. If it takes longer than that, it's a fault. So if you need scan times to be under a certain threshold, then you need, and you can't meet that, sometimes you'll have to design your program a little differently, where you can set up priorities that will force certain programs, certain routines to run more. So allow program priority 1 to finish all the time, but priority 2 can take a little longer. Does that make sense for watchdogs? That's a little more advanced than we need, but the opportunity came up to talk about it. So does that help in finding a location for a fault other than the GSV? I'm gonna create an issue here so this triggers soon. So I can go here, clear major faults. The fault's cleared. You'll see here that the light's back. It's not running though. So you can either put this into run, put the controller back into run mode. Everything's happy, well, except the IO. The run light's back on, and the controller and the logic are back up and running. So back on track. So if we've got a process here, And I'm going to use the example from the controller. So we have let's say we want to do something. We want to do some math. So XIO. So there's a couple of ways to program here. Oh, there's some stuff in here already. Okay. Neat. So as I had said, there's a few different ways to enter in code in ladder logic. So one of the things is if you double click on the rung on the left, you will get this text entry bar, and you could type everything out. When you look at, let's say, this rung, you can double click on it. Now we're editing it because we're online, but this is the single string example of what that whole rung would be. So branch, so BST is branch start, examine if closed, I 62.1, next branch. So that's good. Then saying down one more. So if you memorize the syntax, you can type everything out. One of the things that I do is I'll create a rung, and if I know kind of the general layout of the code that I want, I'll either hit XIC and build what I want by dragging the entities down. So I want a timer for this, and on the next rung, I'm going to have examine if open or examine if closed. You can actually double click on that, and then we're going to add create a new tag, and we're just going to call this timer. So again, you can call this almost anything you want, especially if you're not going to use it anywhere but inside the controller. I don't believe a limit for the length of characters in the tag. But I know Addie asked this question earlier about tagging. You can, if you want to use the tag in an HMI and you want it to be the same from wire tag, from conductor into the program and then into the HMI, one thing to consider would be character limits inside your HMI software. So Wonderware, for example, I believe the character limit for tags is 35 characters, which seems crazy. But if you go crazy with 5 character tag fragments for pump, fault, something with a bunch of I don't know, underscores to separate everything, you can hit those values pretty quick. So here, we're just going to create a reel. We're going to add 10 to it every time. And we're going to make this 5 seconds. So the logic that I wrote, run comment. So every 5 seconds, add 10 to holding value. You can then hit this arrow. It's going to compile all this logic, and now it's running. So you can see here, just like before, like I was saying with the fault logic, The timer testing is not done. It accumulates. So when this hits 5,000 or 5 seconds, it becomes done. And every 5 seconds, this increments by 10. Now, if you were to watch, if the processor and the display were fast enough, you could see this EN bit turning off and back on, but you can't because it's off so quickly. You can barely even see the done bit. You saw that flash there. You won't catch that every time. This routine is completing, the max it completed in is 137 microseconds. And the last, like, these are microseconds. So every scan, so when it's done, that bit is actually only on for as long as it takes to finish that scan and go back up. So it's the EN is off and back on very quickly. That's what I was trying to get to and taking forever to. So you can see the codes running, fault logic here. It's clear. Yeah, there we go. So in the presentation, I was talking about how we will point the program variable. So class instance program, you can get information from a bunch of different classes. So program is your controller, but if you have motion or specific add-on instructions, different types of controller devices, data logging, so you could pull some information if you have a data log to the SD card. I've never pulled information from an SD card, but I have pushed information to an SD card. You can get information from a serial connection. There's tons of information that you can get. Time synchronized. So if you have a sync, like a source, time source synchronizer, whether it's another controller or like a domain controller, you can pull a lot of information from those. Program, main program. So this one is grabbing the fault from the program itself. Major fault record. So you're looking for the major fault record, the last scan time, and the update information of this specific program. And then it's going to pull this specific data type is 11 double integers long. So what that looks like, just gonna cancel this. In the program. So this is in the program parameters versus the controller tags. So I'm not sure if we've touched on this yet. So the controller tags are global. So that means that if you have a tag in the controller tags, it doesn't matter if you're in secondary program, main program, safety task, you have access to a controller tag. But if you have a parameter in the parameters for local tags in the main routine, those are main routine or main program scope only. Meaning if I were here in the secondary program, I couldn't see whatever this gibberish tag is. I couldn't see that outside of this main routine. So if you're, that's why this program, main program fault checker can clear itself, because it's only clearing faults inside of the main program. It's not clearing a controller level fault. We can't clear a controller level fault. Let's say you needed one of these cards. If one of these cards is configured to here, major fault controller on a connection failure, you can't clear that fault. Once that card's faulted, it's gone. And you can't do that from the fault level. Does that make sense? I know that's a little a little inception like with those tag access levels. Okay. So the array, so you here was the main program fault history. Data type is a dint. So we touched on dints, dints, integers. What an array is just multiples of it. So you would have 11 dints in an array. And again, because this is a processor, the first one is square bracket 0, second one is square bracket 1, 2, all the way up to 11. So the major fault record attribute dumps into, sorry, I'm trying to get it to mouse over. Okay. Sometimes when you mouse over, so when you mouse over some elements, you can see how that window pops up. So this is telling me that the tag that I created is a main the name of it, the element type. So the element type I'm on is the square bracket 0, so it's a dint. And I'll talk about, I can't point at it without moving my mouse, but it says the scope and the value of it. When I right click here and go to instruction help, that pulls up a whole bunch of class information. So you can see here with attribute, I was trying to see what the different types are for the different attributes, but as I expected, it's completely dependent on what the information is that you're pulling. So you can see here, depending on your class type and then your instance and your name, your GSV is going to be a different value. So I can't say with certainty what every single one is going to be. It does look like this one is an individual dint, at least what they're pulling, but you could be pulling out strings, integers, any number of things. Are there any questions before I move on about how I pulled this information up and when you might need it? Okay. Anyways, because this logic isn't executing, I'm actually gonna write 0 here, and that cleared it all out. Nothing writes into these values. And you can see here, if I type 1, 2, 3, 4, 5, 6, it'll push it back in here. And because this code only executes in the event that there's a timer change, like a fault, there's no information in that. So I'm gonna hit 0 again, and we'll see what happens here. So I'm going to specify you guys. So I'm monitoring on this page. I can see the fault timer timing. When you look at these with the monitor tags selected, you can see here my preset timer, my timer preset, my timer accumulated, my timer EN, so that's whether it's enabled or not, my timer timing, and my timer done bit. So you can see the EN and the DN inside the call on the main ladder. So you can see the enable and the done. TT means timer timing. So you can't always see everything from this view. Sometimes if you know you have other pieces of information that might be useful in the logic, you might have access to it if you've memorized .tt is timer timing. But if you look at all your different tag types, if you pull these tags up, isn't dint a double word? Yes, dint is a double word. Did I say word at some point?
Oh, I was just confused maybe. It says main program fault history, and then you have the numbers 0, 1, 2, 3. So is that referring 0 as in double word array 0, and then double word array 1, double
Here.
word array 2? Yeah.
Yes. Yes. So this main program fault history is an array of 11 dints. So an array of 11 double integers.
Oh, okay.
So an integer is, a word. So here, square brackets 0 is the first instance of it. So what we're gonna see here is, okay, so this is what I've been building to. I'm going to write a negative value into this preset. This preset is a double integer, but it's not signed. So if I put a negative value into this, that's going to create a controller fault. So then what we should see here, sorry. So what we're going to see here, so this AFI is just an always false. So I don't want it to automatically clear in the event that that's the tag, the one I want. So we'll see, it should see a fault. It should get the fault history, and then we should see information populate in here. So -9. So you'll see that now the processor's faulted. There's a controller fault. Nobody's happy. ACC's completely stopped. EN says it's still on because, and it says it's still timing because this fault just halts everything. The PLC just says, I'm done. It stops. So nothing else is going to work. You could still see inputs. Outputs will typically all turn off unless you have a specific type of card. Do we have one? So if you don't have a card that has the ability to configure program and fault conditions, your outputs are off. So you've lost complete control of your system. You can configure some output cards to do specific things. So in the event of a fault, you could make this output turn on. You could force all of them on, or you could hold last state, or you could allow them to turn off. Default would probably be turn off. Sometimes you would want to force something on if you're in a mining situation or you've got a paint booth or something and you want extractor fans to run no matter what. If the controller faults, just turn fans on to high speed to make sure you're extracting whatever from there. It's normally safety things you would want to turn on, but all your outputs in a fault state, unless they have this feature, are going to turn off. And we can see here, that we populated a bunch of information. So I was right. So when it pulled that fault information out of the fault record, it actually took, there's 6 dints worth of information that it pushed all this into. You can see that? So the one that we're looking for is actually the main program word 2, which is what was said in that presentation. So word 2, sorry, dint 2 is the type and code for that fault. So if we were to break this type and code out, we would find here it'd be a type 4 code 34, which from the presentation over here, oh darn it, I thought it was still open. Sorry if I make weird noises. Type 4 34, a timer instruction has a negative preset or accumulated value. Fix the program to not do that. So yeah, the controller's faulted. So let's say, for example, this is something that happens all the time for some reason, and you don't feel like fixing it. You could hard code that value into your evaluation here. And oh, sorry, it won't let me make these changes while we're faulted. So we'll go over here. We put this back to, let's go 10 seconds. So some of you might realize that I've put 10,000 in there for 10 seconds. So you can clear this alarm here in major faults. You could go up here and you could clear faults as well. If you wanted. Another trick that you can do, and I don't know if it'll work. Yeah, it might. So the key switch on the front of a controller. So this is a trick that I've walked operators through trying sometimes. It's kind of a last ditch effort if you can't get there right away. So you can see here, this says clear major faults. But if you don't have a computer in front of you, one of the things you can do is actually go to that key switch on the front of the controller, turn it all the way to the right, which puts the controller into program mode. And then if you then go back into run mode, okay, it did not work in the emulator. Oh, there we go. So by putting the PLC in the program mode, oh, it might have froze it. Anyways, if this survives what I've just done to it, by going, yeah, there it's running. So by going into program mode, kind of kick starts the processor, so it'll be like it's, yeah, I didn't like that at all. So you can kickstart a processor if it's faulted and it's not a persistent fault. So if it is some sort of control or programming error, somebody entered in a funky set point or preset, or you overflowed. Overflow meaning you've remember when we were talking about integers and double integers, if you have an integer try to write higher than 32,767, it can't, doesn't exist. It'll fault the controller. If you have an unsigned integer try to write to -1, it can't, it'll fault. So if there's a programming issue that caused the fault, you can sometimes put it into program mode and then back into run mode, and it'll kind of wake up And as long as that programming issue isn't something that persistent and it can ignore, what is wrong? That key switch trick will, if I detect it. Yes, I'm aware. Now, why won't you go away? There we go. 22822. There any questions while I'm waiting for this to do its thing? Four warnings, shortened branch. Yeah, okay. So when you compile code, I'm looking down here. I'm just trying to let you know what I'm mumbling about. It's telling me 0 errors. That means that it'll actually compile the code and you can run it, but it will tell me that there's warnings. So here, my secondary program doesn't have any main or fault routines configured because I just kind of threw it in there. So it's telling me it's useless, so I can get rid of it. It'll clear that warning. Warnings will run. It just, this logic doesn't make sense to it. There's nothing going on there, so it doesn't want it there, but it will run. Okay. Yeah. That is angry. Sorry, guys. Oh my goodness. Is that ever angry? Well, there you go. Don't try the key switch trick on an emulated processor. It gets very crappy. And then going forward 0, 30. Let's do its flashy thing. Download. So if you do work in the 500 environment, this auto clearing fault stuff, it doesn't exist. So this is a newer technology. It's a feature. So the 500s, the 5s, the micro logics, they can tell you that there's a fault, but they can't do any of this special fault handling. At least none that I've used. I don't think they've added that feature. All right, so this is running again. I'm gonna go back and look at my fault handling routine. So now we're gonna look and see if, I don't know if this will auto clear that, because that persistent fault, if a -9 goes in here, it's still running. You can see that it's updating. It is. Wow, that's cool. So this isn't gonna run. This timer bit, This timer sub routine is not updated. You can see that, but it's still running the other processes. Everything else is still kind of doing its thing. So like these guys, will they turn on? Or something? Yeah. So there you go. So you can force it to clear that. You can see the force turned on because I forced a bit on. But if I go over to faults, this is the one thing that's kind of one of the reasons why I don't love clearing faults is there's a problem with your code. Something's not working properly. This subroutine is faulted. And because the controller is still running, you're just automatically spamming the reset button. This is like holding the escape button forever on a machine to prevent it from locking up. So yes, you can do this. Is this great practice? I don't think so. It's one thing to maybe clear a fault once or twice, but I'd really not love to do this indefinitely. This could run forever, and if this subroutine were important, critical, safety, this is no longer updating. So you can see again, this is still climbing. I'm assuming what was that breakout for the main fault? I know we pulled that up here. So the first two words, or dints anyway, are time coordinated, and then the fault codes, and then there's 8 dints of fault specific information for this program instance. So you can see there's fault specific information. I don't know exactly what that all is. You could look it up in the, excuse me. Sorry. You could look that up in the manual. Yeah. And then here. So for those of you who have the 500 platform, that's over. Can everyone see that? I don't know if this my share screen is right. Yes, no, you can see the. Oh. Yep. Okay. So you don't need to do any fancy messaging to extract system values. You can actually pull them right out of, statuses. So when you're in the 500 environment, you've got the processor statuses. So it's similar, not identical information that you can get from some of this for fault information and configuration, but you can get your date, time, you can get firmware statuses, so you can know how much RAM is available, how much memory is available. You can get watchdog information. You can get overflow information for different parts of your program. This is rack information, but all of this is available right from the S registers. So if you know what it is you're looking for, you can actually just grab this and use it in your program. So if you need to pull fault information from something, get system time, get update times. There's bits in here that will flash. Here is a major fault code error. You can get some of this stuff. You can't act on it very well because it doesn't have that fault handling feature. It doesn't have that last, like, I see a fault, run a single scan, but you can do some neat things. First scan, average scan time information, and there's a lot. There's even bits in here that'll flash every millisecond, every second, every minute, every hour, every. I think it'll go up to only a month. So seconds, interrupts. So if you need a lot of this information, it is available. You might not have it with all of the descriptions on it. So I could probably send you a copy of a program that has a lot of that stuff pre-described. But you can extract and import that as a CSV. That's just an aside. And then I know I was talking about, again, you've got date and time information, synchronization information. If there's other processors that need to synchronize time, you can set up where the one I'm looking for here is. I don't know if they have it. Okay. Let's see if I can pull that up. Sorry, that was a little anticlimactic. Let's do. So this is now local VM I have on my machine. So there. So when you have an actual controller configured, you have this could you? Yeah, if you could share a sample code through Conestoga. I think I can. Yeah, I'll ask my chair what I'm allowed to share, because some of that stuff that one specifically belongs to the city of Guelph, but I'm fine with it. I just don't know the rules, but I should be able to post it somewhere. So I was talking about the SD card for faults and for the light on the front of it. So you can see here under non-volatile memory, can't do anything with it. That's annoying. What do I got? Sure, go online. I need that program. Sorry, there's a control. Where's my program? That's sorry, guys. Yeah, pain in the butt. While I'm walking through this to show you this is the RS Links driver. This is how you communicate with controllers. you can set up different networks in it. If you need help looking through one of these, I can help troubleshoot. I set up different networks for different clients when I had my programming laptop. The one that's only here right now is my home, but let's say I were to go to Hagersville, whatever. Inside here, it's not configured. You can, yeah, there we go. You can pre-configure all of your controllers inside your driver. That way, when you go to the site, you just need to change your computer's IP address. And then you'll be able to see and then connect into it without having to configure that every single time you need to. So if you need help looking through how to do that, by all means, ask some questions. New project. L61. Sorry, guys. I always think something's going to take less time than it does. EXTRUD. It's in 17. When you do make programs, you at least for control logics, you need to make sure you get the rack size right. You don't necessarily need to configure all of the cards, but you have to get the rack size right. Come on, I just did that. Oh. Okay, so now oh, because there's not a card in there. So I thought there was a SD card in that processor. I apologize. This is if there's an SD card in there, you can load and store the program. And I wanted to show you what that looked like in configuring what they can do. So does anybody know what an EEPROM is? That's kind of a throwback to microcontrollers. I know one of you went to Guelph for computer engineering, and I think Tatiana, you're a software engineer. Do you know what I mean by EEPROM? Yeah. So the 500s and the older PLCs and some of the RTUs, it's the SD card works like an EEPROM where it will store a program in it, and then when I believe the way it works is when you trigger it, it'll load the program into the microcontroller. So the SD card for the control logics and the compact logics can be configured to do something similar. So you load it with the program, and on power cycle, it can load from SD card. On major fault or minor fault, it can load from SD card. It's a really powerful and it's a really useful tool, but again, it can be a double-edged sword, because you're not, if you set it up to do it on a fault and the system's been running for years, and you make changes, you add a new card. And I've had this happen where an electrician there'll be an upgrade on a processor, and they add in a new card, and the programmer programs a new card and programs new subroutines. And then down the road, somebody faults the controller. It grabs an old program, it loads that program in, and then because it loads an old program that didn't have the new IO card, it then faults the controller because the IO didn't line up. And now the controller will never run, no matter what anyone does, without bringing a programmer in. So it can really cause issues. So if you ever come across a processor that's faulting for a reason that you can't explain, even if you make changes to the program, double check to see if there's an SD card. Okay, that is everything I've got to show you guys today. Sorry, let me just... Yeah, so we covered a lot. So we went through normally open and normally closed contacts. Pretty straightforward stuff, I think. If there are any questions about that, let me know. Some of their uses, again, normally closed, typically used for safety-ish devices, things that you need to see are in a state all the time. So for a fire alarm or a heat alarm, or strain gauges, or we're looking at safety bars and safety systems where as soon as it's activated, it opens up a loop, or you've got multiple switches. So like e-stops or safety stop buttons, those will be normally closed contacts, so that if you hit any one of them, it'll open the circuit no matter where you've hit it. Normally open contacts, start buttons, light switches, momentary push buttons, yeah, things that you only want to see when they turn on. Pump overloads, as long as you're not looking to use the overload status inside another circuit. For PLC statuses, those are your normally open contacts. And then we got into different types of faults for the controllers. So we've got minor faults that don't necessarily fault the controller and don't halt the execution of code. So some examples of those, you can get IO faults, would be minor faults. A battery, if the battery dies, that could show up as a minor fault. Or the battery is low. That is something you'd want to take a look at. If the battery's low and then you do lose power, you might lose your program. The battery keeps the circuitry that holds the memory on. So like anything, replacing the battery is important, but the processor can normally still look at things if it's just a minor fault that doesn't require or doesn't halt the code. But you can program the system to extract fault codes with the get system values and reset or clear specific faults, which I showed you here. Looking up fault codes, the easiest place to find them, in my opinion, is going to be here, especially if you've got a laptop for troubleshooting. Yeah. There are things you can do. So I know Tatiana had asked about logging fault codes. So You could log a fault code, but you're going to have to program that yourself. So inside the fault routine, I'm trying to think how I've seen it done. You would end up having some move commands. So you would, when there were a fault, take the last fault data you had, move it into another array of information, and you'd have to create, I would imagine you'd have to create a custom data table, which would have an array with a time for the last fault, the code for the last fault, and then kind of push your timestamp back. So you might not necessarily be able to, like, you could see the last 50 events, however big you built your data arrays. But as long as you ordered it inside your fault handling routine, you could definitely kind of increment and step back where the top entry would be the most current fault, and potentially the time information that you would get. As I think these words, these two dints are associated with the time and maybe ladder. You'd have to really dig into the manual to figure out what that information is. And this information, and then your actual fault code. Does that make sense? Am I helping there, Tatiana? Yes, perfect. I've seen some municipalities do it, but they do it, they will do it up here. So as an aside, and I think it doesn't, we're not going to be able to cover it without actual processors. So you can try this if you have your own physical processor. But here under the controller fault handler, it will, you can actually program, I have to go offline to get to these. You can create a controller level fault handling routine. And then it'll do the same thing, only again, where we have the different scope levels, it will run one step above. So if there's a fault that's above the main program, you might be able to catch that fault up here and clear it. So that might be, you might be able to clear some faults from communication modules. If you've got robots that throw faults for whatever reason, whenever they home or whenever they power off, or your controller is configured to produce and consume tags in a funny way that periodically have issues. I might be saying things that you don't understand, and if you don't, I apologize. We don't cover some of them, but if you've seen them, you know what I'm talking. Like you'll know kind of what I'm talking about. Those are going to be controller level clearing, as I don't think the emulator runs properly with those. If it does, like I don't know, it didn't like my key switch thing, so I might play with it a bit, and I might try to get something set up on my actual controller here. But yeah, so that's kind of that's everything I had for this week. There's no assignment. There is a quiz and some additional reading material if you guys want to work through. I'm going to work to get the last of those assignments graded either tonight or tomorrow. Yeah, and I will talk to you guys next week, and those in tomorrow I will talk to tomorrow. I'm gonna stick around for the next 20 minutes, so if you've got any questions, shoot. If not, have a good night. Thanks, Scott.